Okay, good afternoon, everyone. We continue today with our lectures. Today we will talk about the electric fields from individual charges and visualizing electric fields. So, what is the definition of an electric field? An electric field is defined as the region of a space that is around a charge where that charge influences this space such that if you bring another charge closer to this charge, it will feel an exerted force on it. Now, it depends on the value of the charge that you are bringing. The direction of the force will be based on with respect to the direction of the electric field. So, this electric field is a vector based such that at any point surrounding that charge that we are studying, the electric field generated by it will have a magnitude and a direction such that they are visualized as arrows going either toward that charge or away from the charge based on the value of this charge. If this charge that is generating the electric field is positive, then those arrows will be going away from that charge. If that charge is negative, then those arrows will be pointing toward that charge. Now, the electric field at a distance r from a single charge is given as E equals to K Q magnitude divided by r squared. So here is the magnitude of the electric field such that this is the magnitude. To calculate the magnitude, the direction is based, as I said, on the charge. If the charge is positive, then the arrow is pointing away from the charge. If the charge is negative, then this arrow of the electric field will be pointing toward the charge. The unit for the electric field is newtons per coulomb. So, as I said, this electric field is generated because of that charge that I am here giving as capital Q. If I want to calculate the force that will be exerted on a charge closer to this charge that is generating this electric field, then the relationship is given as F equals to Q E, such that if that charge that I am bringing closer to my charge that is generating the electric field, if this charge is positive, I will see that the induced force will be in the same direction as the electric field. Now, if you think about it, if this charge was a negative charge, then the induced force will be in the opposite direction of the electric field, as we will see later on. So this is how we visualize the electric field around a positive charge. As I said, they will look like arrows, and those arrows are pointing everywhere. If the charge that is generating this electric field is positive, those arrows will be pointing away from the charge. If the charge that is generating the electric field is negative, then those arrows will be pointing toward that charge. So, as I said earlier, it is very important to understand if I bring, let's say, a positive charge here, let's assume that Q1 is positive, equals to E, then the electric field based on this expression, F equals to QE. If E is pointing away, then definitely the force exerted on this charge will be pointing away as well. If this, so here the electric field agrees with the force if the charge is positive. If the charge is positive, then the electric field, the force induced on this charge agrees with the electric field in the direction. Now, if this charge is negative, based again on this expression, the force will be in the opposite direction than the electric field. So the force will be pointing this way. Now, again, if we apply this also on the chart, in the existence of the field for a negatively charged particle, the same expression applies. If my charge that I am bringing closer here is positive, then the force induced will be in the same direction as the electric field. If the charge that I am bringing closer here is a negative charge, then the direction of the force will be the opposite of the electric field. In all cases, this expression has to be valid. Now let's look at this example. Here we have an electric field at a distance of 1.9 10 to the power minus 8 meter from an electron. So the charge that I am evaluating the field generated by is an electron. In this case, the electric field generated by this electron will be pointing toward this electron. So this is the electric field. This is the electric field. At any point, it will be pointing toward the charge, the electron. Okay. Now I want to evaluate the electric field right at this point. That is at a distance of 1.9 10 to the power minus 8. Now what I've drawn here is the direction of the electric field. If you think about it, based on this expression, the electric field is Q magnitude divided by R squared, which means if I am to draw the electric field at that point, it will be, for example, this way. The closer I come toward the charge, the stronger the magnetic field. Look at it this way. So there is a field at every single point such that this field is pointing toward the charge. The closer I come, the stronger the magnitude will be. However, at any point, those are the direction. At any point, it will be pointing toward the charge, the negative charge. However, at any point, there will be a field. The magnitude will become stronger the closer I come toward my charge that is generating this electric field. Okay, so I need to evaluate the electric field right here at this point. So in this case, magnitude is 8.99 10 to the power 9 times electron, taking magnitude, which is 1.602 10 to the power minus 19, all divided by 1.9 to the power minus 8 meter squared. And the electric field E is 4 10 to the power 6 Newton per Coulomb. Now this is the magnitude for the electric field at this point. The direction is toward the electron. Now if you want to verify what I have just said, try to calculate the magnetic field right at this point you will see that the magnitude is stronger. The direction is the same toward the electron. However, the magnitude is greater than this magnitude. Okay, so let's move on. If we want to evaluate the electric field due to calcium ion that has lost 2 electrons, that's why it became with 2 positive, equivalent to 2 charges at a distance of 1.9 to the power minus 8. If you recall, the electric field we calculated was due to an electron, which basically will use the magnitude. Now this one is going to be doubled. That's why here this is positive. That's why the electric field will be pointing away from the charge. However, the magnitude will be doubled. So just very quick calculation. We had for 1 electron at the same distance, we had it 4 10 to the power minus 10 to the power 6 Newton per Coulomb. The charge has been doubled, then now the new magnitude will be 8 to the power 6 Newton per Coulomb. However, because it's positive, it will be pointing away. And the answer to this question would be D. So that's what we were discussing earlier. If I have this field generated by this point charge, this particle, then as long as my charge is positive, the force will agree with the electric field in the direction. If the charge is negative, then the force would be the opposite. The force would be the opposite of the electric field. So this is very important to remember. Always take this expression, they take this equation to lead you toward the correct direction of the electric force. If you have an electric field generated from positive charge, then this electric field is pointing outward, away from that particle. If the charge that you're evaluating this electric field on is positive, then it will agree with the direction of the electric field. If that charge that you are evaluating the electric field on is negative, then it will always be the opposite. Just substitute this Q with negative, and you will see that the force will be in the opposite direction of the field. Okay, so more examples here. What is the electric force experienced by an electron? F, it is 1.9 to the power minus 8 meter from another electron. So we have an electron that is generating an electric field, and we said in this case, because it's an electron, the electric field will be pointing toward this electron. So we have minus E. And we have another electron that is sitting somewhere here at a distance of 1.9 10 to the power minus 8. So if we calculate the electric field at this location due to this, then the electric field, let's start this way, then calculate the electric field right at this point, then the electric field would be 8.99 10 to the power 9 times 1.602 10 to the power minus 19 divided by 1.9 10 to the power minus 8 squared. And we found that the electric field at this point would be 4 times 10 to the power 6 Newton per Coulomb. 1e with the same distance, we just did it, 4.4 to the power 6 Newton per Coulomb. Now, if I want to calculate the force at this point, then I need to use this expression, F equals to QE. Now, if my Q here is negative because it's an electron, then definitely the force will be in the opposite direction than the than the field. So the field here is pointing toward this charge, then definitely the force here would be in the opposite direction. So this is going to be the force, right? And then F would be minus 1.602 10 to the power minus 19 times 4 10 to the power 6. Then F would be 6.5 10 to the power minus 13 Newton, and will be pointing away. Why pointing away? Because the field is pointing toward the electron, and this one is negative, then the force would be in the opposite direction. Then the force here would be in the opposite direction, right? Okay, now let's do the other example here. So in the second example, the question is asking, as we've read earlier, what is the electric force experienced by a proton if it's 1.9 to the power minus 8 meter from the calcium ion? So my ion here is the ion that is generating the field is positive. In this case, the electric field will be pointing outward this way because it is positive. Now I need to evaluate the force experienced by a proton. So I brought a proton somewhere here, and I know that the distance between this calcium and the proton here, which is equivalent to 1e, is 1.9 10 to the power minus 8 meter. So in this case, this is positive. So let me put the equation. F equals to QE. As long as my charge, which is this one, is positive, then the direction of the force agrees with the direction of the electric field. Well, I know my electric field is pointing outward, then definitely the force here will be pointing also outward because it has to agree with the direction of the electric field. Now, if we want to calculate this magnitude, then this magnitude would be K. We'll find first the here K KQ divided by R squared, where we have the electric field right at this point equals to, we said 8. If you recall from what we've done in the previous two slides, Newton per Coulomb. So this is the electric field right at this point. Then the force is 1.602, a positive, 10 to the power minus 19 times 8, 10 to the power 6, right? So this is E, this is F, then F equals to 1.3 10 to the power minus 12 Newton and pointing outward. So this is the magnitude. If you want to put the vector, then you say 1.3 10 to the power minus 12 meter pointing outward. Okay? So this is how we calculate the force due to a charge that was brought at that location that we know the field at. Now, one thing you need to pay attention to and be careful of as the difference between the electric field and the force. They are not the same. The electric field exists everywhere around a charge, doesn't need to have any other charges. So the electric field can exist with the existence of one charge. However, a force will have to have at least two charges. There's a big difference. As you can see, or recall, electric field is generated due to the existence of one single charge. One single charge will create this electric field in the space around it. However, the force has to have two charges at least in order to Q times E. Q times E. You have to have at least two charges in order to have a force. If you don't have two charges at least, then the force at anywhere surrounding that charge will be zero. So if there's no charge, if Q is zero, then the F would be zero. Let's look at this example. In this example, we have an electric field, both magnitude and direction, at point D. That we need to calculate. So right here at the point D, we need to calculate both the magnitude and the direction of the electric field due to what? Due to two charges. The first one, Q1, that is minus 1.21 microcoulomb, and due to the Q2, that is positive 3.4 microcoulomb. So let's calculate that electric field at that point. So here we have Q1, Q2, where this is 30 degrees, Q1, Q2, Q1 is negative minus 1.21 microcoulomb, Q2 is positive 3.4 microcoulomb. This is the point D. The distance here is 6.83, 10 to the power minus 6 meter. The distance here is 3.19, 10 to the power minus 6 meter. We need to calculate the electric field at this point. So let's start first with the electric field due to Q1. We know Q1 is a negative charge. What does that mean? This means that the electric field at this point will be pointing toward that negative charge. So this is E1. However, Q2 is a positive charge, and the electric field due to Q2 right at this point will be pointing away. So this is going to be the electric field due to Q2. Let's start. First, the magnitude of E1 is, again, K Q1 over R1 squared. So we have E1 as 8.99, 10 to the power 9 times Q1 magnitude 1.21, 10 to the power minus 6 micro is minus 6 divided by 3 0.19 10 to the power minus 6 squared. So in this case, E1 is 1.07 10 to the power 15 Newton per Coulomb. This is E1. E2 is 8.99 10 to the power 9 times magnitude of Q2, which is 3.4 10 to the power minus 6 divided by 6.83 10 to the power minus 6 squared. E2 is 6.55 10 to the power 14 newtons per Coulomb. So I have now E1 and I have E2. I need to project E2. So if I assume that this is my X, this is my Y, then projecting E2 on the X and Y, this one would be E2X, and this one would be E2Y. So if this is 30 degrees, then this one is also 30 degrees. So E2X equals to E2 times cosine 30, which means that E2X is 5.67 10 to the power 14 Newton per Coulomb, and I have E2Y as E2 times sine 30 degrees, which means that E2Y is 3.28 10 to the power 14 Newton per Coulomb. Then EX, E total X as E1 minus E2X, E total X equals to E1, which is 1.07 10 to the power 15 minus 5.67 10 to the power 14. E tot X is 5.03 10 to the power 14 Newton per Coulomb. This is the X component, and the Y component will be coming only from the E2Y. So we have here E2Y would be minus, so E tot y will be minus 3.28 10 to the power 14 Newton per Coulomb. Now the total would be E tot would be the square root of 5.03 10 to the power 14 squared plus minus 3.28 10 to the power 14 squared, and now E total would be 6 10 to the power 14 Newton per Coulomb. The angle is theta is tan inverse the y component, which is minus 3.28 10 to the power 14 divided by 5.03 10 to the power 14. And the angle is minus 33. Theta is minus 33.11 degrees.